I get confused because Archana is Saksham, no?
Yes.
Hello, Saksham.
सेकंड में वहां रखो ना.
हाँ. Guys.
Today, Aryan is wearing a Himachal Pradesh. I think that's
Yes, sir.
Himachal cap.
Yes, sir.
I also have one.
सब पापा गए थे.
Earth is the cricket match also.
Yes.
Hello.
हाँ.
उदय जी आजकल आप कहाँ पर हैं अभी?
अभी मैं यहाँ डार्टमouth मैसेचुसेट्स में हूँ. मैं
कहाँ पर?
एक जगह है, इसका नाम है डार्टमouth, DARTMOUTH. ये बॉस्टन के से 60 माइल साउथ में.
Oh, it must be very, very cold, ना?
हाँ, यहाँ पिछले 15-20 मैक्सिमम टेम्परेचर 0 के नीचे ही रहा है. मैक्सिमम, मिनिमम तो काफी कम है. और आज स्नोफॉल है, तो फिर कल स्नोफॉल उसी दिन होता है जिस दिन टेम्परेचर ठीक अच्छा होता है. और उसके बाद फिर जैसे कल आज स्नोफॉल हो जाएगा, तो कल जो है मैक्सिमम टेम्परेचर है -7 एंड मिनिमम है -14. और इसमें कम से कम 10 डिग्री तक आप फील लाइक लगा दीजिए, क्योंकि अनलाइक इंडिया यहाँ कोई हिमालय नहीं है, तो आर्टिक विंड जो होती हैं वो सीधा आता है, कोई भी पहाड़ नहीं है आर्टिक से लेके यहाँ.
अच्छा.
Yes, sir. Sir, I want to give a presentation. Sir, should I give it?
Yeah, go ahead.
Yes, Aryan, you are.
Okay, sir. So, sir, my presentation is about quantum physics. So, then today I will be talking about the different quantum phenomena. So, introduction to quantum electrodynamics. So, it is the quantum theory that describes the interaction between matter and light matter through electromagnetic forces. It combines quantum mechanics with special relativity, explain electromagnetic phenomena at the atomic scale. So it is fundamental in understanding the behavior of photons, electrons, and their interactions. So for the first phenomena is spontaneous emissions. So it is the process by which an excited atom emits a photon and transits to a lower energy state without external influence. It results from the atom's interaction with the vacuum fluctuations of the electromagnetic field. So this process is probabilistic and categorized by a specific of the excited state. So this happens when an electron in a lower energy state emits a photon and goes to a higher energy state, and then it goes down, releasing another photon of uh, of the energy that was the energy difference from the two energy states. So the photon's energy would be the energy of the higher state minus the energy of the lower state. So and the electron stays there for about 1 to 10 nanoseconds, and then it goes to the lower energy state, and in that it wobbles, which signals the electromagnetic field to start creating that photon. So a quantum description of spontaneous emissions. So it models spontaneous emissions as a result of the atoms coupling with the quantized electromagnetic field. So the atom's field interaction causes the atom to emit a photon spontaneously. So the role of vacuum fluctuations. So vacuum fluctuations are temporary changes in energy that occur in empty space due to quantum uncertainty. So these fluctuations induce transition in excited atoms leading to spontaneous emissions. So they are an essential aspect of the quantum vacuum. So people believe that they are one of the main reasons for these spontaneous emissions. When that electron is in the highest energy state, it gets bumped by these vacuum fluctuations, which then uh, transits to a lower energy state. So, ladies and gentlemen, any questions right now? Okay, so let me get
Anybody
to the.
have a question? Earth, do you have a question on this? Hello, Earth. Earth thing is showing a cricket match going on.
No, sir.
No?
That
So
is
do you
just a
have,
background.
oh, that is just the background.
Yes,
You have
sir.
any question on what?
No, sir.
Okay, go ahead.
Okay, sir. So, a breaking radiation concept. So, it refers to the emissions of photons during atomic transitions, effectively breaking the energy gap. So, it is a spontaneous process, a construct with stimulated conditions which require external radiation. So, we can imagine it has that we are running as fast as we can. So, when we uh, so at that time we have a lot of energy because we are moving so fast, but if you suddenly had to stop or we have to take a sharp turn, we would feel a very big push. So electrons feel that same push when they zoom past a big atom. So what happens that in free electron, when it gets way too near a nucleus, it gets deviated from its path and then it creates photon to recover the lost energy. And if the electron gets captured, it will become a a standing wave near the nucleus and orbit it as the other electrons do. And if that happens, it would release a lot of energy as in single photon, like of an X-ray or a gamma ray. So, in the quantum world, an electron never stops like a car would. If a fast moving electron passes near an atom and breaks to a full stop, or as close to a stop as it can get, it must get rid of all its momentum energy. It releases one single high energy photon containing the energy that was lost. So, why is it so special? So, unlike the quantum jumps, where light only comes in specific colors, breaking radiation can create any color or energy of light depending on how much the electron slows down. This creates a rainbows of X-rays called a continuous spectrum. The faster it slows, the stronger the light it creates. So it's a very easy situation we can imagine had has an electron going near an big nucleus, and because of the electrical forces, it deviates from its path, and the lost energy is then created to photons to make up for that lost energy. And if the electron gets fully captured, it will release a very high energy photon and then become a standing wave near the nucleus and will be trapped in the nucleus. Uh, will be trapped around the nucleus. So, what would happen if the electron stops? So, an electron never stops like a car would. If a fast moving electron passes near an atom and breaks to a full stop, or as close as it can get, it must get rid of all its movement energy. It releases one single high energy photon containing all that lost energy when a free moving electron stops zooming through space and gets trapped by an atom. It stops looking like a little ball and starts behaving like a cloud or a standing wave. So that was the same scenario that I said. So quantum state evolution during emissions. So on the quantum level, this evolution of a state during emission is a complex transition where an electron moves from an excited to a lower energy state, simultaneously creating a photon. This process is not continuous but follows a specific mathematical and physical path described by quantum electrodynamics. So, when an electron begins to emit light, it does not simply disappear from one orbit and reappear in another. Instead, for a brief period, it exists in a superposition. So, when that specific electron absorbs the energy of that photon, what happens? It jumps to a higher energy level state, and when it is going down, for a brief moment, the wave function of that electron is an hybrid of the high and the low energy state, and at that time it also starts to wobble around, which signals the field around it to create that photon. And I think so at that particular time the photon is also quantum entangled to that same electron for some time, so that they can conserve momentum. And at that time it is an hybrid, and after that happens, it releases the photon and then goes to a, and the wave function goes to a the lower energies. So before the photon is fully released, the atom enters a state which is where it is both excited and not excited at the same time for a tiny fraction of a second. The electron cloud wave function is a hybrid of high energy shape and low energy shape. During the mix, the electron could actually vibrate, wobble at specific frequencies. This wobbling is what shakes the surrounding electromagnetic field to start forming the photon. So that is what happens. The electron starts to wobble around, which signals the electromagnetic field to start forming that photon, and the photon's energy level will match the energy of the high energy state minus the lower energy state. And for that amount of time, specific period, the wave function of that electron would be an hybrid of high energy and low energy shapes. So it enters a state of superposition at that time. So quantum entanglement. So before a photon is fully released, the atom state and photon states are linked like two ends of a string. If the photon is heading left, the atom must feel a tiny kick recoil to the right to keep everything balanced. Instead of a straight line down, the state of the atom diffuses or drifts randomly through different possibilities like a leaf falling from a tree. So, as I said, that before a photon is fully released, the atoms and the photon states are linked, they are entangled, quantum entangled, which means if the photon is heading left, the atom will feel a tiny kick recoil to the right to keep everything balanced. So, ladies and gentlemen, any questions? Sir, do you have any questions?
Yes, yes. Aryan, but I really appreciate, I mean, how at your age you are able to understand all these things. I
I
really appreciate.
so
Very good, very good. हम तो क्लास 12 तक क्वांटम मैकेनिक्स का नाम भी नहीं सुने थे.
sir, it also took me an entire month to try all of this. Yes,
Yeah,
Yes,
but
very good.
what you should do is that, the each statement that you make, there is a physics in that.
yes, sir. So that is why I included the quantum entanglement superposition. So I still have many more questions. Like my questions are not answered. So there are many questions that I cannot answer and I don't know the answer of.
It doesn't matter, but you are getting a feel of what it is.
Yes.
So, but now you should just spend a little bit time, everything that you must know it, go to the deeper roots of it, what
Yes.
it is, But then you have really, I appreciate very much.
Yes.
Oh,
Sir.
I wish you all the best in your life.
Yes.
उदय जी आपका क्या कहना है? उदय जी
मैं कह रहा था काफी
हेलो.
सारे चीजें इसने यूज किए हैं इसमें, जो अपने आप में एक प्रेजेंटेशन लायक हो जाता है.
Yes, sir.
Yes, that is what I'm saying. Yes. It is great, really. हम हम मेरे समय तो क्लास 12 क्या, मैं तो सोचता हूँ कि जब मैं ऑनर्स में गया तब मुझे क्वांटम मैकेनिक्स वर्ड मेरे कान में गया.
Yes.
क्लास 12 तक तो हमने क्वांटम मैकेनिक्स वर्ड ही नहीं सुना था.
क्वांटम
एवरीथिंग लुक.
एंटेंगलमेंट, सुपरपोजिशन, ये सारे चीज को एक एक्सप्लेनेशन बन जाता है.
Yes.
Till class 12, no, I thought that the world is really very, because everything was classical mechanics, no, so it looked very simple and nice. It's only when I entered honors, then the problem started. कि अरे ये तो बड़ा मुश्किल का चीज है ये तो. और मेरे जो फिजिक्स के टीचर थे, क्वांटम मैकेनिक्स पढ़ाते थे, he was also a very nice person, so he used to teach in a historical manner. So that used to make he used to make it very interesting, that historically how the ideas developed. तो मुझे काफी इंटरेस्ट लगा.
Sir, Saksham has a question.
Yes.
Saksham has a question, sir. He has raised his hand.
Oh, Saksham, yes, please go ahead.
Hello, Saksham.
Yes, Saksham. Hello.
Okay.
Yes, Saksham, go ahead with your question.
Okay. So I think so. He has some problem by his side.
Mhm.
Sir, his mic is on, but he can't. His voice is not getting to us.
अच्छा, गले में कुछ खराबी तो नहीं है?
Uh, sir.
Hello, Saksham. Is your mic okay, or is your voice box in you okay?
Okay, so I think so, sir. I should continue, and we will take last. Okay. So, sir, spectral lines, shapes, and line width. Every time an atom bumps into another while it is trying to shoot out a photon, the color of the flash gets messed up slightly. If there are a lot of bumps, the line looks very wide. This tells us that the gas is dense. Like in the atmosphere of a giant planet, electrons only stay in their excited high energy state for a tiny amount of time before they snap back down. Because this time is so short, the laws of quantum physics says the energy of the light cannot be perfectly exact. There is always a minimum amount of fuzziness. So what it says is spectral lines. So if we look at something like a gas, and if we get it spectral lines, what will happen that we can find out what it is made up of, and if the lines are very wide, we will know that the atom has bumped a lot of times before shooting out that exact photon, and then we can say that the gas is very dense. So this is one way to understand what elements are there in a specific material by looking at its spectral lines. Okay, so summary of key concepts. So spontaneous emission is a fundamental quantum process explained by quantum electrodynamics. It involves the atom's interaction with vacuum fluctuations and the electromagnetic field. So, controlling this radiation has profound implications for technology and fundamental physics. So, yes, sir, we are done with the presentation. So, any further questions?
मीटिंग चल रही थी
Yes,
So,
you have a question?
चल रही थी
sir, Saksham is raised
Yes,
his hand.
yes. Saksham, now are you able to speak?
Hello, sir. So
Hello,
my
sir.
voice is clear now.
Yeah, I can hear your voice now.
Okay, sir. So I'm having a question that we know that there is
Hmm.
365 days in a year, right?
पेंशन दी है ना
365 days.
Yes, sir. In our Earth, there is 365 days in a year, right?
Right.
Yes, sir. Then you can say in leap year, why we count 366 days?
Okay, so uh, why that happens is because it is not exactly 365 days, it is also 6 hours. The 6 hours are also included. So, to keep all of that in account, after every 4 years, we get an extra day.
एक year
Okay.
Yes. Sir, do you have any questions?
No, I don't have any questions. Rather, I'm going to read them through once again. I try to understand some of the things that you have said.
Okay, sir.
So, in my case, when I was more interested to work in quantum mechanics, but I got an opportunity to work in electromagnetics.
Okay. So, sir, I think so. Electromagnetic electromagnetism is also very hard topic. So when I started studying astrophysics, I thought about reading about the four forces. First of all, I learned about gravity and the other forces, the strong and the weak nuclear force. But I could not understand electromagnetism. It was pretty hard for me. So I also still have some many problems with the topics.
Yeah, we'll take one by one all of them. First, we will take the simpler ones. If you have a very simple question in electromagnetics, which even Earth can understand and Saksham can understand,
Yes.
okay, let's welcome Mukesh. Hello,
Okay.
Mukesh Ambani.
ना कर देना
Okay.
Hello, hello, Mukesh Ambani ji.
अच्छा वो तो नहीं है जोधपुर से ज्वाइन किया हाँ
जी मुकेश अंबानी ज्वाइन किए हैं.
वो जोधपुर से तो नहीं ज्वाइन किया देखो
Sir, I think so. He has joined from Jodhpur. I think so. It's his second time joining.
his name is धीरज
His name is Dheeraj. I think so.
Dheeraj.
Yes.
Dheeraj, why don't you say something about yourself?
Sir, he left it.
Oh, yeah.
Yes. So, yes.
So let's go to now. Saksham, do you have any question?
Sir, I want another. There is another question that we know in a leap year there is 366 days, right?
Right.
And we also add extra one day in February, right,
Yes,
sir?
Yes.
that is how you make it 366. No?
Yes, sir. But why we add extra one day only in the February, not only in April, March?
No, it could have been added anyway, any month. It's just a choice. So
Yes.
some months that 31. And okay, this is a historical fact. One could have chosen a very different way of doing it.
Yes.
So there is that must be a historical thing why he chose only February. पहले जमाने में मंथ्स वगैरह जो होता था ना राजा डिसाइड करते थे you see.
Yes.
In the beginning, before this 12 months, there used to be only 10 months. That's how our numbering you see has become. October was earlier the 8th month, but now it is 10th month.
Yes. Sir, here is
So the kings they पहले decide करते थे. So that is how it has happened, you see, and we are following it, and there is no change in that. But other calendars follow in a different way, actually. You have Indian calendar, you have Chinese calendar, you have calendars.
Add some
He has joined. Udayji, you want?
because last few centuries the Europeans have started dominating it. So we started following the Roman calendars, this thing, and they were against month where months were 29, 31, and so on. So when the correction took place, they removed 1 day from February, and that's what. The second thing is, it's not actually 365 days and 6 hours. It's 365 days, 5 hours, 48 minutes, and 46 seconds. So the correction happens in such a way that every fourth year is a leap year. By doing this, you are adding more number of days than actually should be. So every 100 year, which is also supposed to be a leap year, is not a leap year.
Oh,
And
yeah,
because
yes.
of this, and it comes now there are less number of days. So the millennium year is again a leap year. So there is a lot of playing around they do to match this particular figure.
Oh, yeah, yes, yes. Yeah, that's very correct. But in my school, that the teacher taught how to know which month will have 30 or 31. So they taught us like this on this one. In this one, so you
Yeah,
count from this
nakal thing.
one. First one January, next February, March, April, May, June, July. So all the raised ones, these raised hands, they correspond to 31 days. And the hand if you have, you see, from this one you can, if you forget which one is 31 and which one is 30, you can make it out from this. I don't know whether the king also, Udayji, do you know why this is so? Actually, the king also decided in this way or what? Using the hand. It is very surprising. It matches with the.
नहीं जब 29 रहे थे तब
And regarding October being 10th month, actually January, February were 11th and 12th months. So
Oh, is it so? Oh, I see.
yeah, in the Roman calendar, January, February were added, and their year was 355 days, not 365 days. So because of all this, when the correction took place, a lot of things got rehashed. Even the April Fool is because the year was starting from 1st April initially. So when they made it to 1st January, there was reluctance. Now the narrative was that anyone who's not following is a fool. That's why the April Fool thing started. So a lot of changes has happened in the English calendar over last few centuries. And because they were the dominant force in last few centuries, everyone is forced to follow their calendar.
Oh, that's very interesting. I didn't know this. Yeah, very good. I think Udayji, you have got encyclopedic knowledge.
No, no. The financial year could be anything. in India, we followed that British system, and that's why it's first April. In US, it is 1st January. So the financial year, it was only initially everyone followed different financial year. The government was following 1st April. So during Rajiv Gandhi's time, they actually changed this thing and they made 1st April for everyone. So a lot of changes have happened in the way we look at things. And now, initially, when the budgets were used to happen at 5:30 in the evening, it was only during the Bajpayee government when they changed it, the morning. And the Modi government made it 1st February. Because so that state governments can also have some reaction time and the budget allocation happens by time 1st April comes, so that they have better idea how to divide their budgets.
Oh, you mean
So
1st February? 1st February.
Yeah, the budget started 1st February because the state government, initially the state government is to, they never knew how much money they are going to get. So they is to estimate that last year we got so much, so next year I'm going to get this much, or this year, and they used to have their own budget. Then the budget is to be recalculated because the center budget is to come later. It was end of month, February 28th. So they made it 1st February. And initially the budget announcement is to happen at 5:30 in the evening because the Britishers used to do. It continued till time Atal Bihari Vajpayee became the Prime Minister. He changed the time. Because 5:30 in the evening, 5:30 in India is 12 p.m. in Britain. So there used to be simultaneous presentation of budget both in India and US, in Britain, till independence. But Britishers left, the mentality continued.
Oh, I see. I see. Now things are getting clearer as to how. Yes, Aryan, you want to say something?
Yes, sir. Sir, I had a question. So,
Yes, go ahead.
so sir, whenever we walk on ice, why is it slippery?
Because the ice contains water.
So, like, what
No,
happens with molecular structure that is moving, uh, that? So, I am asking the main reason in like molecular structures. How is that happening? Because it is just in solid rigid. It is just in rigid body ice. Why is it
No,
happening?
actually, ice also has
I
water.
think
Yes, sir.
No, go
yes,
ahead,
yes,
please.
Udayji. Udayji, please go ahead. Yes.
No, I'm saying why ice has a water. Any liquid acts as a lubricant. So water also acts as a lubricant. So it reduces friction. Since there is less friction, friction is necessary evil. It's required for us to survive. So when the friction is reduced, it becomes slippery.
So, and I had one more question regarding friction. So, sir, is
No,
like,
no, actually, there is, Aryan, the friction always is if the surface structure, if there is a what you call unevenness, the more the unevenness, the more the friction. Now,
yes.
suppose any kind of course, the in case of the ice, it is not exactly crystalline, but more or less crystalline. So structure, I guess, I'm not very sure. I guess
So,
that unevenness reduces in that case. Basically, that is what friction is.
sir, I had one more question. So, is there something more fundamental that gives rises to friction?
No, fundamental this only, the unevenness of the surface. So
Okay,
at the microscopic level, or even any structure, if you see, they are not very smooth. So
okay.
friction basically arises from that, actually.
So, sir, one more thing I've read somewhere. So whenever we throw something in space, like a rock, why does it slow down?
Whenever you throw a
When
rock
yes,
upward,
no sir, in space, why does it slow down?
Sir, can I try
yeah,
to answer this question?
yeah, go ahead.
Sir, so whenever we throw something into space, it slows down because it is free of every everything. It is free of every kind of forces.
So
No,
the
no, it's because of the. No, are you telling Aryan that if I throw a stone upwards and then it slows down? Is that what you are asking?
no sir, like if I throw a rock in space, why does it slow down?
Yeah, that is
I
what I
think
am
because
saying. That
it is free of
if I
gravity.
throw a rock, it will upwards. If I throw the word slow down means the speed increases or velocity decreases. You means velocity decreases. That is what you are asking.
Yes sir, why
What
does
do you
that
mean by
happen?
slow down? Because of the gravitational force, there is a
Sir, but
force
there is
acting.
no gravitational force in space.
There is no space anywhere where there is no gravity. Wherever there is zero gravity, like one of the
Like
satellites which is now parked the L1 and the L2 space. That is the place where almost the resultant gravitational force is zero.
so, like
So that is why they have
sir,
parked it there.
so sir, like a place where there are no massive bodies, and where if we throw rock, it will slow down. So sir, why does that happen, and where does that energy go?
No, no. Theoretically, it will not slow down. If there is no gravity, if there is no force, external force, any force acting it, it will keep moving. Actually, I think you are confusing between throwing in the air, what we normally do, and space. In space, if there is no gravitational force nearby, it will just move at the constant speed. That's what the Newton's first law says.
Sir,
Yes.
sir,
But
I'm
there is no space where there is no gravitational force in
sir.
general.
So sir, I was reading about Einstein, and it it was a problem that he was facing. So he had to give the conservation laws for his general theory of relativity. So he could not find those, and and there was a person, David Hilbert. He looked at his problems, and he found some it wasn't part of it. I'm forgetting. So says that energy is conserved only in an empty static universe, and I think so. There was one more major physicist involved, Emmy Noether. So I think so. She solved it using her symmetries, and she said that symmetry gave rises to these conservation laws, and uh, our universe does not have one uh, important symmetry. I think so. Time. It was about time translation symmetry. So what is that? So let me give you an example. So let's imagine that there is an empty static universe, and if we throw a ball at a ball, it's, let's say, it travels 100 meters. So what we can do is that we can move the whole universe 100 meters so that it goes to its original position. So our universe does not has that. So that means it does not have a symmetry, and this that symmetry was responsible for the conservation of energy. So that gave rise to the conservation of energy laws. But our universe did not have that specific type of symmetry which said that uh, it does not conserve energy at large time scales like our universe. And so there was one more thing, general covariance. So where it is also like a symmetry. It is a local symmetry. It says that everywhere in the universe the laws of the gravity would be same. So that is called a local symmetry, and that is why, like, we people, if we throw something, the laws of the conservation, the laws of conservation will act upon that, and that is why when we throw something like a rock in space, it slows down. And where does that extra energy go? It just simply disappears. So, and for that, if we have to get an conservation law for a specific patch of space time, what we have to do is to we have to get we have to also add the curvatures of space time. So yes, sir, that was what was so this problem was about the conservation of laws. So it was a problem. It was a problem faced by Einstein, which was solved by Emmy Noether. So by doing that, she just told that our universe is not symmetric and does not follow the laws of conservation of energy, but it has local symmetries. So that is why in our daily lives we see that these laws are being followed, but on a universal time scale, they are not being followed, and the extra energy, it just disappears. Yes, sir.
Aryan, your statements are too difficult for me to understand.
Sir,
I'll take
sir,
time to understand them. I'll take time to understand them. Anybody has a comment on this?
sir, Saksham has
Yes,
raised his hand.
Saksham has a comment. Yes, go ahead, Saksham.
Sir, I have a question that how does gamma ray bursts help us to find the large and distant objects?
Now,
Okay.
what is a gamma ray burst, by the way?
Sir, gamma ray burst, you can
Hmm.
say, is a kind of explosion which occurs when two neutron stars collide or a supernova or a hypernova explosion occurs. It releases a so lot of energy, even more than the entire lifetime of the sun.
That is true. That is true. So, what was your question?
So,
So,
sir,
why
my
does
question was, how does gamma ray bursts help us to find large, massive, and distant objects?
Oh my God, I can't answer this question. Anybody has an answer to this question?
Oh,
So, sir, I think so. What we can do is that if we detect gamma photons somewhere coming from a direction, we can just uh, point our telescopes at that particular direction and try to get something. So, sir, if so, those gamma photons are of pretty high energy, and if we find anything, we can speculate that it was from a very high power explosion or something pretty powerful.
Yeah, but all of you, do you understand that? How, okay, so this we discussed long time back, but maybe we can repeat it a little bit. That why does, how do we know this red shift? Do you understand?
Yes, sir.
Yes.
Oh, sir, one more
Sorry.
thing.
Yeah,
So, sir,
but
I was talking about that how the laws of conservation were not being followed by the universe. So, let me give you an example. So, the CMBs were photons, and when they reached us, they lost about 99.9% of their energy, and that is an example of the conservation of laws not being followed by the universe, and so that extra energy just disappears from the universe. So I just gave an example. I had read it on an article.
oh,
Sir,
I'm going to
sir,
check
but I
it.
did not get satisfied with my question that how does gamma ray bursts help us to discover large, massive objects?
By discover, what do you mean? That is, to locate the position of that?
Yes, sir. Like we discovered Hercules Corona Borealis Great Wall.
Yeah, I think give me some time to find an answer to this question. How does, if anyone knows, we can say, how does gamma what is Saksham asking?
Actually, I don't know. I'm just trying to make an attempt because it is actually very high frequency, very small wavelength, and high energy. It is able to penetrate through the cosmic dust and give you information which is the other side where we normally we can't see it because of the cosmic dust. So it passes through the cosmic dust. We are able to capture it. We know that it is coming from some object, some star colliding or supernova, something collapsing, something is happening, which creates gamma rays first.
Sir, I think that if gamma ray burst is very concentrated in a particular area, then scientists might discover the large objects. I think so.
Yeah, you are right. So first thing is they are able to detect gamma rays, and they are able to detect gamma rays because it's able to penetrate the cosmic. So I think 1995 or something. Before 9, I don't remember the year. They used to only look for space where they used to get some information. During that period, they actually focused Hubble in a totally different direction where they could not see anything, and they found something totally not aware till that time. So every time we are trying to discover things. So gamma rays only prompts you there's something happening. So start looking for it because universe is so vast you can't look across the universe. You have to look into a pinpointed area. Gamma rays to that extent actually helps to guide you where to look for.
Yes. So, Uday sir, I had something
And
to say.
also the intensity, because of the intensity, one can pinpoint it.
Yes.
The gamma rays, all the time, some gamma rays are also coming, but when the burst is there, you get the intensity also increases. So that is a pointer to that collision has taken place. Okay, that is very commonsensical, but what Udayji has said is also correct.
Yes. So, Uday, sir, had a question for you.
But
So, sir, sir, what are your views on the breaking of conservation laws on the universal time scale?
can you
Do
elaborate slightly? What do you mean by breaking of conservation law?
so, sir, like our universe is not following the conservation of energy laws on a very large time scale. So, it was a problem faced by Einstein. He could not get the equation for conservation of energy to say that the energy is being conserved in his theories. So he could not get those. So there were many physicists who tried to solve his problem. So one of them was Emmy Noether, who who used symmetries to help explain that symmetries gave rise to conservation laws, and our universe does not have a specific type of symmetry which states that our universe does not follow the these laws at very high time scales because of the expansion. And the reason we are seeing that these laws are being followed on our scale is because of one more thing called general covariance. It states that the laws of gravity and other things would be same everywhere in the universe. So it was the basic principle of relativity. So that is also called as local symmetry. So in a specific, like in my room, the laws of conservation of energy are being followed because of this local symmetries, but they are not being followed universally. So That is why when we throw a rock in space, it will eventually slow down. So that extra energy just disappears.
Yeah.
Aryan, somehow I'm not able to, understand the idea of what does the disappear mean actually.
So let me explain it again, sir. So Einstein faced a problem.
No, no,
Uh,
something disappearing means what? The
so, sir,
energy
it
has
just
disappeared.
vanishes.
Now,
Sir, it
what is the meaning
vanishes.
of that? What do you mean by vanishing?
Sir, uh, sir, anything just completely like it is gone from the universe. It goes nowhere. It just simply disappears.
How is that possible, by the way?
Sir, it is in these symmetries that if we understand these, we'll know what these laws actually mean.
Now, this is understandable that there is because of this local symmetries you have conservation laws. But something disappearing is a very interesting thing that
Yes.
I don't know how to explain it and how to understand it also.
Actually, I can try an attempt. I don't know. Uh, First of all, Einstein equation that E is equal to mc square has been proved wrong long time back because it does not factor in the wave theory. It only assumes that everything is a particle. So the moment you introduce wave, that equation itself moves, it changes. Now, when they are talking about, okay, so now initially when I got disconnected, there was some talk about that
Yes.
cosmological constant. So
Yes.
now there was a Christian belief that everything is universe is there is one earth and earth is surrounded by a sky where everything is fixed. So things moved until that time everyone believed that the universe is static. The Einstein equation actually came up with this thing that universe is not static. Now it is classic case when you decide your conclusion before your experiment and then you tailor your experiment to meet to suit your conclusion. So conclusion is universe is static. My equation does not support it. So I introduce a constant to make it static. Hubble actually proved him wrong. So when Hubble actually observed it, that things are moving, and that's how they came up that Big Bang theory. That okay, if it is expanding now, at some stage it would have been small, and now they have done this. Now that theory over a period of time kept getting revolved. When they got more information about Milky Way, they found that if the universe is expanding, then the stars in Milky Way should be thrown out by centrifugal force. But that's not happening. They are being held together. So why they held together? They said, okay, there is some gravitational pull. They call it dark matter, which is pulling everything and keeping everything together. So now the next concept came: if everything is together, then they should collapse. But they're not collapsing; they're still expanding. So
Yes.
they came up with dark energy that everyone is moving away. So now in this particular case, when you talk about there's something called redshift thing. Now, when universe is expanding, the energy is reducing at the rate of hv by lambda. So here it is the photon which is getting removed. So this is not particle. That conservation of energy was E is equal to mc square. One energy is transformed into another. It does not factor in the wave part of it. Because of wave, some energy is getting lost. That is the current analysis of it, and that's purely, I think, because of the concept of wave particle theory.
Okay. So, sir, like from the like the light that we have received from the CMB, so at that time when they were first created, how did they lose their energy and where did that energy go?
You're talking about the Big Bang theory?
No, sir, like the light that we have received from the CMBs, uh, they are in microwave radiation. So where did that extra energy go?
Light from micro. What type of light you are talking about?
Sir, if there is something that is very far away and it releases light, and when it comes to me, it would have lost its energy. So where did that extra
Okay.
energy go?
Yeah. Where did so first of all, the scientists are still debating about the dark matters and dark energy. What is happening to them? We don't know. It's called dark because it's mystery.
Yes, sir.
Okay. So yeah. So when the light, uh, they were able to correlate this that when the energy is lost, the wavelength changes. Because the wavelength changes, and the change they are also attributing because of the various gravitational pull happening all over the place, which is changing the path of the that particular light, which results in change in their wavelength, which results in change in their color. And I think I don't remember the year. There, I think 1995. I was talking about this time, 1995 Hubble Deep. They
Sir,
actually found out. They found out a galaxy which was beyond another galaxy. So the only way the light could have come through them is by circumventing that particular thing. Means light did not follow a straight path. It followed a path which was slightly curved because of the uh, gravitational pull by the intermediary galaxies around it.
yes.
So, what is the dots? Okay, so that's what they were talking about. I think
So,
redshift is about the same thing.
okay, so sir, I think so. You are saying that, like, if I'm getting an equation and it is wrong, we introduce an Hamilton. I think so. It is an a known value that accounts for everything else, and it is an like excuse to make the equation correct. So I think so. You are thinking that. I think so.
Yeah, that's what it happened that time. When Einstein's, first of all, science is a evolving phase. Whatever is true today could be false tomorrow. It's not
Yes,
because the person is lying, it's because he has only limited knowledge.
yes, sir.
So as we progress, we get more and more information about universe, and we realize that whatever we thought last time to justify our explanation is not correct. So at that moment when he introduced that constant, in fact he called it a blunder, because as per him the universe should have been expanding, but because everyone thought that universe is static, in order to create the universe static he introduced that constant.
Yes. So, sir, the thing that you have just said, the starting the words. So this reminded me of why we say theories instead of laws. So like the laws of Newton, we say to give homage to him, uh, but they were also wrong. So it's in theory, and if we have tested that law to its extreme and to its extreme, like near the sun, near many massive objects, so that would have become a law. But now we call them theories, and if they are tested to their extremes, then it gets the status of a law. So we just say that Newton laws just to pay respect and homage. So yes,
Yeah.
Oh, no, Aryan, it's not like that actually. What happens is that in science, we make a theory based on certain observations.
yes, sir.
So suppose I have got 10 observations and I make a theory, and that theory explains those 10 observations. So we accept it that
Yes,
it is working and it is explaining 10 things. Now the next day what happens? Another observation comes. Now that cannot be explained by the present theory. So you have another theory which is still better, but that doesn't mean that the previous theory was wrong. It had limited this.
yes, sir. We
It
have to
was
test
correct,
it
and it
at
was
use.
limited. It was limited, and now this is broader and more general. Same thing is with the Newton's law. It's not that the Newton's still people who send rockets they use only Newton's law.
Yes,
So it is correct. It is correct, but then it is not very correct. There is something still better, you know. So
yes,
that is how science works. So that is why we don't throw away like say Newton's law. We don't say that it's wrong.
yes,
But it has a limit correction, it needs a small correction. It needs. I mean, there is something better.
Yes.
It is just like that. And there is one thing I wanted to say, Udayji, sometime back when I was in the atomic energy, so when Penrose got the Nobel Prize, then after getting the Nobel Prize, he visited India. He gave 3 hours lecture in our office that what happened before the Big Bang. But
Sorry,
they were all,
who came to
yeah,
India?
Penrose.
yes. He came to India. He came to India. He came to our office also. I had the
No, who?
privilege of showing him.
Can you repeat
Yeah.
the name of the person?
I had-
I missed that
Roger
name.
Penman.
Hello?
Penrose. Roger Penrose.
Yes.
Okay.
Who got the Nobel Prize, this
Okay.
recently. So recently means a few years back. I had the privilege to show him our cyclotron here, so he was impressed a little bit because in his mind the impression was that in India the science hasn't developed yet and things like those kind of things were there, but he was impressed. So in the talk that he gave, he told that he doesn't believe that the universe started with the Big Bang. There was something else before the Big Bang. But it was too highly mathematical, so mathematical that after people started yawning after some time because it was so mathematical. But it was very
So,
interesting. Who
so,
knows? Tomorrow it may come out that what is we might get past this singularity someday.
so, sir.
Because it doesn't make sense that the time also should start at that time. There was no time before that. These are the statements we make now. But in future, when people like Aryan and Saksham, when they grow big, they'll come with a new theory which will tell us what happened before the Big Bang.
So,
Very
sir.
interesting.
So, sir. I like you have met him, Roger Penrose.
Yeah, just showing him the cyclotron around. That's
Okay, sir. So, sir, I had a question. So, it is about the fields. So, what is the difference between potential and potential energy?
Potential is supposed to be to do with electricity, and potential energy is height.
So, sir, what I understand potential is that if we have a single body in space, its potential would be counted as I forgot. I just forgot the law of Newton. It would be the laws of it would be its gravitational field, and for an uh, potential energy, it would be two systems and their gravitational fields. So I understood that only.
The potential energy is supposed to be mgh, isn't it? Mass into gravity into height. So the primary thing is water falling from the tanki down.
Yes.
It reduces its potential energy and gains its kinetic energy. So that's how it's supposed to be. And then it hits the ground, it converts into heat energy, water. So that is the transformation of energy that takes place. And potential is supposed to be to do with electricity, that potential difference of the voltage difference.
yeah, same thing as you're correct actually. No potential and potential energy. Potential energy is really the difference actually. Suppose there is an electric field, then I want to draw lines, where the potential, let us say, whatever the force or whatever it is, same. So you draw a line, so that is one potential. Then you draw another line. So those are the places, points of potential. But the potential energy which is there is related to charge into the potential difference. That's the energy part of it.
Yes, sir.
So that potential thing is used in the magnetic field also in some way, in the gravitational field, in the electric field.
So, sir,
the something like the lines of force concept which
yes,
originated
yes,
with
lines of
field,
force.
yes, it is
So,
like that. That concept kept on getting added up.
sir, it came to
Every
my
time,
mind.
wherever there is a field, has a potential.
Yes. So,
Wherever
sir,
there is a field, there is a potential. Every
so, sir,
point.
sir, it came to my mind when I was reading another article. It was about
Mhm.
how electrons change their behavior because there was something like a non-existent force, and I think so. It has to do something with potentials, etc. So I think so. It went like if we point a laser in space, and
Mhm.
if the laser is made of electrons, there can be a deviation in it. So they explained using potentials and other things. So I didn't read the full article, but it was about this only. So Saksham has a question, sir.
Yes, Saksham, go ahead.
Sir, I have a question that what is the difference between galaxy superclusters, galaxy filaments, and you can say galaxy walls?
First you have to, the difference I won't be able to say, but then you have to explain to me what are these things.
So, sir, these are a group of galaxies. So, a galaxy supercluster means there are a lot of galaxies in one space, and galaxy filament means like a part of the observable universe. I think so. I That is
No,
what I
no,
understand.
no. Galaxy filament, you consider the group of superclusters.
So, yes,
Yeah, and
that would be a small part of the observable universe where there are a lot of galaxies.
yeah, if you look, they look like a line, along the length, line. Those
Yes,
clusters are there.
yes. In between
Yes,
there are
sir.
voids.
Galaxy.
And the clusters.
Yes, sir.
So these are just names. These are just the names. How they are formed and how they formed. Okay, that is something we will get to know in future.
Yes. So, sir, like when an atoms does spontaneous emission, like the electron absorbs the photon and it releases an photon. So, does it heat the material then? Sir, did you get my question?
I got your question. One thing, okay, I haven't earlier I've tried to explain this question, but let me just try it out. Udayji, if I'm wrong, just correct me.
Oh, sorry, I
No,
didn't get the question. Sorry. What is the question?
what
So,
he says is that if there is an emission, spontaneous emission is there, then does the matter get heated up? Now, when you say heated
Emission
up,
from which emission from
now
where?
one thing is there that suppose in the inside, let us say an atom emits in this one, and if it gets absorbed by another atom, of course that will lead to some heating that is there. But is that the question you are asking?
yes, sir, it came to my mind because I saw a very reflective thing, and I was wondering that when it absorbs the photon, it then reflects back. So during the process, will that material get superheated?
No, let's not use the word right now superheated. Just say heated. Let us say that means the energy. So if the energy which it emits, it gets absorbed by the matter itself, by another atom or something like that, there will be some heating will take place. Yes, of course. As a matter of fact, if you remember the radioactivity thing,
Yes,
which Madame Curie and Pierre Curie, they,
yes,
they had kept a radioactive atom inside their pocket, a radioactive substance, and they felt actually. If you
So
read
it
the
was
history, they felt the heat, because that radioactive, they didn't know that the radioactivity is being emitted. So
yes,
they felt the heat and they got a burn, in fact.
yes.
Their skin got burned actually, just because they kept in the pocket.
So, sir, like when we push a
Small
lot of
observations, they carry a lot of physics in them.
yes, sir.
Around you in your house, you look out for them. Very small things, there is a lot of physics in it.
Yes, sir. I always keep wondering about these things. So, like one more question I had: when we push something, there is some bunch of matter and push it. So why does that get heated? Is it because the atoms are getting closer? So, how is that happening? I still did not get it.
Uh, Udayji, what would be your explanation? My explanation is no, that if you are pushing it someone, so the heat exchange will take place, but just by the pushing itself, if you are distorting the material,
Yes,
if
sir.
the push ends up in the distorting the material, some heat is getting generated. That's true.
So, sir, if it's because the we push the atoms and the molecules close together, so
Yes,
like
it
so
distorts, but if there is no change of shape or anything, all that, I don't see that anything will happen.
so, sir,
No,
like so the is the heat being produced by the electrons that push them farther?
if if I understand your question, you are talking about applying pressure to something, let's say gas, and closing them together. Are you talking about that the pressure is applied, volume is reduced, and temperature increases? Is it something to do with that?
It was a little more simpler. So when I push something, how is that heat being created and
I think
how
he is talking about the solid materials.
what's that?
I've not understood the question completely. If you're only talking about solid material getting pushed and getting heated, it could be because of friction. Okay. If you're compressing something, then the only thing is those atoms are colliding, vibrating with each other, which generally happens with gases or maybe to some extent liquid, where you can compress them to convert them into solid.
Okay, sir.
So, is it that the question? Which is basically simple law where the volume increases, decreases, temperature increases.
Oh
They
yes,
are inversely.
yes, sir.
So now I think we are coming to the end of it. So I have a question for Aryan and Saksham.
Yes, sir.
So very, very simple question actually, and maybe you could ask your friends also that on the earth, if I am standing on the North Pole,
Yes, sir.
then my head is up and my leg is down.
Yes,
But
sir.
someone who is standing on South Pole, his head will be down and leg will be up. Is it?
Head would be. Yes, I didn't understand the question.
You didn't understand it? No,
Yes.
but on the earth, suppose I am standing on North Pole. So I look up, so my head is up and my leg is down. But it is a spherical body. So there is a person standing on South Pole. So his leg will be up and head will be down, isn't it?
So, sir, I think so. It's an question about it is we are just changing our frame of reference, and that is the effect happening because we changed our references that we got to one place and the other one.
What does Saksham say? Saksham, what is your answer to this?
Yes, sir. What is your question?
My question is that if I stand on North Pole, so my leg will be down, my head will be up. But a person who will, if you go to South Pole, then your leg will be up and head will be down, is it? Is it true? Do you agree with this? Or let me put the same question in slightly different way.
Okay, sir.
Suppose I am in the North Pole and I look at the moon, and suppose if someone is there in South Pole and he looks at the moon, will he see the same structure or will it be different?
No, sir. It will. I think so. He will see upside down.
What does Saksham say? Saksham?
So, according to your question, that if you
Mhm.
stand on the North Pole, your head will be up and your head will be up and leg will be down. And if you stand on the South Pole, your head will be down and leg will be up. I think this claim
This is
might
correct or incorrect?
be false.
Huh?
Sir, regarding how do you feel it, I think this claim is false.
Yes, sir.
No,
So,
this
sir.
is false.
Yes, sir. I think that's because the gravity is local on Earth and
So,
due
sir.
to relative orientation, etc.
So, sir, like if we look from the point of view of the Earth's core, we will see that our legs will be down and our heads will be up. So, it was just about the phrasing, I think so.
And what about the moon structure? Moon, will he, the North Pole man and South Pole man, will he see the same moon?
Yes, sir. He will see the same moon.
Yeah, but Aryan says no, he will see something different. So both of you fight it out. Who is correct?
So not that same. You can say that in the North Pole we may see that the moon like you can say normal, but in
Moon
the
is
South Pole we might see the moon tilted
Yes, sir. That was a
the
at
moon
perfect.
is
the 90
tilted
degree angle.
90 degrees. But
Yes,
why
sir,
90
90
degrees?
degree.
Why 90 degrees?
So that's because it is
Sakshi has
circular
made a
and we are
very
seeing it from the down.
well. I didn't understand why it should be 90 degrees. I was thinking 180 degrees.
लगता है तो टूटता
Yes,
है
sir, 180 degrees. And that was my mistake. It will be 180 degrees.
Okay, okay. So I think we have now come to 9:20 and Pankaj ji is already now wants to close the session.
Yes.
So wish you
So,
all the best.
yes.
Yeah, Uday ji, thanks. I think you have got encyclopedic knowledge. Very nice. I think to
Oh
have
no,
you.
thank you.
Yeah. Our children, you see, they are very bright. You see, they are
Yeah,
asking questions.
I fully agree. They are brighter than we were at least 10 years older at their chase.
100% I agree with you. I wish we had some more children like these in our group.
Yes.
I, Saksham, you want to last question? Okay, what is that?
Sir, I have a question that we know that the Indian Ocean is the hottest ocean in the world, right?
I didn't know that. Anyway, if you're saying I'm accepting it, then
Yes, sir. So why do storms grow much stronger in Pacific and Atlantic Ocean compared to Indian Ocean?
oh my
Okay.
God, that's such a
Okay.
difficult question.
So, sir, I think
I
so.
never thought of it.
So, it
Is
hasn't.
it Atlantic Ocean has more storms?
Sir, you can. Sir, my question is in Indian Ocean, storms grow typically average at category 3 or 4 and winds with 240 kilometers, right?
Okay.
I
But in
accept what
Pacific
you
and
say.
Atlantic Ocean, the storms frequently grow at category 5 and even exceed the winds of 300 kmph. So why is it so even if the Indian Ocean is the hottest?
Sir, I think so. It may be because of the surface area, and when that water gets heated, the hot air rises up and the cold air takes its place, so that generates a current. And if it happens for a longer time, and if it has more area, this process will happen faster, and this will result in a bigger storm. So that is my guess, sir.
Yes, certainly.
Okay, so he's
Yeah. But anyway, I'll have to try to understand this question and answer to this.
yes.
No,
So
another
we,
thing is, so can I add
yes,
something to this?
yeah,
Okay.
One is
sure,
the
sure.
orientation of these oceans.
What is
Okay, orientation. The Indian Ocean is more east west along the equator. This is more north south. That is one reason. And second is between both India, Atlantic as well as Pacific, for long stretch of land north south, there is no landmass, whereas there is no such thing for the Indian Ocean. And for storm to build up, it depends on the for a tropical storm for India, the sea temperature has to be around 27 degrees. Temperature is around 27 degrees, the storm will initiate. So only if now, I said earlier, for the Indian Ocean, there is something called ITCZ, Indian intercon ITCZ convergence zones in tropical convergence zone something. So now that is like a thermal equator that moves up and down the equator as the sun direction moves. So as that thing moves up, the second thing is there has to be a land mass and a water body. The more the water is able to collect, or for longer duration, the storm is over the water, it becomes bigger. They are just drawing water from this. That is not true in case of like when we get a storm from Bay of Bengal. There is not enough water body there for it to pick up water. Before it can become bigger, it is hitting the landmass. Whereas in case of Atlantic, the hot air from Sahara is moving towards the Atlantic, picking up water, travels all the way to US. So it has a long distance to travel. It becomes bigger, collecting a lot of water into this, and that's how it becomes more powerful.
Sir, but as
Thank you, Uday. I
earlier
think
Ines
you
has said that
given
the
us.
Indian has not so much area to build up this cyclones of reaching 300 kilometers, right? But if the storm is coming from, you can say, Madagascar and traveling towards Pakistan or Arabian Sea, then it can reach the 300 kmph winds.
You also have to factor in the rotation of the Earth. The most of the storm moves from west to east.
Okay, sir, you said that
In monsoon season, most of the storms are from west to east. There are very few from east to west.
okay, sir, you said west to east. Then, in case of the gap
Sorry,
between
I stand
Australia,
correct. From east to west. It is from east to west. It is westerly direction from east to west.
yes, sir, as you said from east to west, then the gap between Australia and Madagascar, or you can say the Australia and the Somalian plate, there is enough space to get a storm which can reach a speed of 300 kmph. Like the
Australia.
typhoon Haiyan, which got so much winds in such a less time.
No, you also have to consider the thermal equator. The thing is moving up and down 23.5 degrees. So as the temperature moves to the northern hemisphere, the storm will be in the northern hemisphere. When the thermal equator moves to the southern hemisphere, maybe in winter, then the storm will move there. So you can't connect an object in southern hemisphere with an object in northern hemisphere. Now Australia is in southern hemisphere, so it has to be in the southern hemisphere around that particular thermal equator, same latitude. You have to talk about the latitudes. There is
Yes,
a
sir.
latitude difference.
Yes, sir. In the same latitude, like Australia to Madagascar or Australia to Mozambique, their storms can go and can reach a potential winds of 300 kmph.
Okay. The other okay, like I give you example regarding Sahara. The hot air has to blow from Sahara to the sea and carry this thing. So what is the trigger there? Where will the hot air come from? You are saying the Australian deserts?
Yes, sir.
I'll have to find out why it's not happening that way and whether they are in the same latitude.
Good. I think we had a good discussion. I think Udayji has told us many things. And thanks for the nice question.
Yes,
So
sir.
now we'll close because it's 9:30 now.
Yes.
And wish you all the best. Have a nice weekend.
Yes.
Thank you, Udayji. Amarnath ji
Oh,
came
thank you
and
so
went
much.
away. Is he
Yes.
still there?
Yes.
Oh, yeah. It's very cold where he is.
बोलो सर को कुछ बुक्स
Okay.
Okay. Have a nice
Bye.
weekend.
You too. Bye.